Hello everyone and welcome back to my channel. In this video, we're going to solve 10 problems. I will give you timestamps so that you can jump to the level that is appropriate for you. So before I start solving these 10 problems, I want to remind you something really important here. So whenever you have a conditional statement, and you can choose whatever specific example of a conditional statement that you want, because going forward, I'm just going to be using if P, then Q, where P is an antecedent and Q is a consequent. But if you want a more real life example, I have given you one here, but you can come up with your own. But what I want to remind you and really highlight here is that with conditional statements, order of antecedent and consequent matter. What I mean by that is that here I was trying to come up with a contrapositive truth tables, right? So I'm trying to build it piece by piece. I need not Q, where I have Q here. So I wrote not Q as the first column and then not P. Okay, that's fine. But if you wrote not P like I have here and then not Q, that would be fine too. However, you need to remember and really be alert to not do this sort of thing, okay? Because the way I have here, I went in that direction. But if you switched the columns of not P and not Q, then you would need to remember which one is antecedent. And how do you know? Okay, antecedent sits before the single-sided arrow, okay? I will repeat. Antecedent goes before this arrow. So think of this as a container or a spot, or this is a chair, okay? That's a chair where the antecedent sits. And this is chair where consequent sits. So whenever you look here, oh, okay, this is antecedent. Whenever you look here, oh, okay, this is antecedent. And then you go this way, okay? So you're looking for when antecedent is true and consequent is false. That's where the whole thing is false. Not here, because in the correct order, you would look for that. So anyway, don't let that confuse you. So now I'm going to start solving problems. First, let's start with level easy. All right, first problem is asking us to identify antecedent and consequent, and that is simple enough. I don't even read this. I just know that anything that comes after if has to be antecedent. That's a spot where antecedent always goes. And this has to be consequent. Question number 2. What can be said about the truth value of Q when P is false and if P then Q is true? You don't know how to answer that question. What you know though is to build a truth table. So don't think about it on a raw without a truth table. Get the truth table and then think about it. So write down what you know. What you know is that with a conditional statement, this antecedent and consequent are true. The whole statement is true. Then it's false, true, true. So then you find yourself a spot that they are telling you. So P is false, okay? So these 2 rows here, because that's where P is false, okay? So the last 2 rows. And see if they're giving you like ability to narrow down, and they're not. And the entire statement is true, they're telling you. So, okay, we're in these 2 rows, and therefore we don't know the truth value of Q, because truth value of Q in these 2 rows is either true or false. But truth value of any statement, any proposition, is either true or false. So that's not any information to say that, oh, Q is either true or false. Of course it's either true or false. What else would it be? It's a proposition. So in this case, you will write down not enough information, or it can't be determined, or you can't say much. So I'll say not much. All right. By the way, if they gave you when P is true and the whole statement is true, that would be enough information to say something about the truth value of Q, because they gave you one single row. So you narrowed down. But in this case, they didn't. So that's what we're going to say. All right, question number 3. Which of the following conditional sentences are true? So here they're asking you which row, these are the conditional statements, which row do you find yourself? So if hexagons have 6 sides, okay, this is antecedent and it is true. Let's see what is consequent. Then the moon is made of cheese, okay? This is false. So what can we say? When antecedent is true and consequent is false, we find ourselves in a second row and the entire statement is false. Okay? Then second example, if 7 plus 6 is 14, and we know it's not, it's 13. So this is antecedent and it is false. Well, I don't even have to continue reading because I can already narrow down. I know that the entire statement when antecedent is false has to be true. It's trivially, necessarily true. So anytime antecedent is true, you have the whole statement being true necessarily. So I don't have to even read the consequent. So the whole statement is true. This actually happens to be true too. So we are, in fact, in third line. All right, now moving on to the next level, medium difficulty. All right, fourth question. Make a truth table for if P, then Q and P. All right, what can you identify from the get-go? First of all, you can't answer this question in your head. You have to produce a truth table and you stop thinking, you just write down what you know in truth tables. And you notice that you have 2 different sorts of propositions. So you already know you only need 4 lines, not 8. So I write down 4 lines and I know I need to produce this logical unit. Right now, it has some statement there, but after I get truth tables for that, truth values for this whole thing, I'm going to start treating it as one logical unit, just like P. So I'm not going to have anything different than if P then Q. So I'm going to start treating that as one whole logical unit. And how do I come up with truth values of Q and P? I have conjunction. I know how to come up with truth values for conjunction. Conjunction is and connective. So it's similar to when I say I want chocolate ice cream and vanilla ice cream. I need both for me to be happy. Okay, if you give me only one, I won't be happy. So conjunction is true where both conjuncts are true, when you get me both flavors of ice cream. All right, so I look at conjuncts here and it's only true here. Everywhere else, it's false. All right, done. I have produced truth values for this. So I forget that there is Q and P there and I start treating this as one logical unit. You can call this if P then M. And you look at this and then you treat this as antecedent and you apply the same rules that you know. When antecedent is true and consequent is false, that's where the whole conditional statement is false. I always first look at that because that only happens once and everything else will be true automatically. So let's first find where it's false. So antecedent is true, consequent is false. It's false there. Everywhere else, it's going to be true. All right? So these are the truth tables. They asked you for truth tables and you've given them truth tables. So moving on to question number 5. Show that the following are logically equivalent. Okay, logically equivalent means one thing and one thing only, that they have the same exact truth values. Okay, otherwise they can't be logically equivalent. So you need to get truth values of this statement, then truth values of this statement, and compare and see and hope that they are the same exact thing. All right, first thing that you need to notice is that who's participating. Who's participating? P, Q, and R. 3 different variety of propositions or statements. There are 3 different flavors. So you need 8 rows because there are 8 different unique ways to match them. Okay? So I have written the ingredients, but we're going to do the logical stuff together. First one asks us to come up with P and Q, conjunction. This is and, right? So P and Q, I know that it is true only when both of them are going to be true. So it's true in the first row, it's true in the fifth row, and that's it. So I'm first going to write where it is true. Okay, there. Now I'm ready to produce the first statement, which is I'm going to start treating this, since I already have truth values of this, I'm going to start treating that as one logical unit. So if P, then R. Or if A, it's not reuse the same letter, then R. Okay, this is A. And you just look at this. And notice that this whole thing is sitting where antecedent would go. That's a spot for antecedent. So you're going to go like this in this direction. So you're going to try to find where antecedent is true and consequent is false. Okay, this, and that's it. This is the only spot where it's going to be false. Everywhere else, it's going to be true. So you can just write down trues everywhere else. Is that true? Yeah. Now I need to come up with not R, and that's very simple because if I have R, then not R is going to be inverse of what I have. So false, 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 and true, 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 true. That's not R. And now I have to come up with P and not R. So now I'm looking at this column and this column. And in first 4 rows, I know that conjunction will be false because I need both of them to be true at the same time. Remember, I need chocolate and vanilla flavors. So here, they're going to be true. And that's the only place where they're going to be true. Everywhere else, I write down false. Now I need not Q, and that's very easy to generate. So now I'm ready to come up with the whole thing. So I have this thing, and now I have this as well. So I'm going to start treating this as one logical unit and this as one logical unit. So all I have here is if P, then Q. So I will just go by the rules that I know about conditional statements. So I'm treating this as an antecedent. So this is in a spot of antecedent. Okay, so these are my antecedent truth values. And this is consequent. So what I'm looking for is where is antecedent true and consequent false? Okay, and that's the only place. All right, so this is false, and everywhere else it's going to be true. And at this point, I am done. The original question was show that the following are logically equivalent, that this produces same exact truth values as this would. So I have done the truth values of the first one, and let me highlight where I have those. I have those stored here. And then I've produced truth values for the second one. And if you see that they look identical, and they do, then you've shown that they are logically equivalent. And also, notice that same as, I have if and only if arrow symbol here, double-sided arrow. Okay, that is a mathematical symbol for same as, also known as, because this means logical equivalence. Logical equivalence means the same truth values. Question number 6. Give an example of a true conditional sentence for which the converse is also true. So they asked you to come up with a conditional statement that is true, and then to make sure that its converse will be true as well. I'm not a fan of this question, but I included it in this video because it's tricky. And I really done considerable amount of thinking about this. And the reason why I'm not a fan of it is because if converse is true, that means that, so if P then Q is the original. The converse will be if Q then P. And if that's the case, then they should have used if and only if, double-sided arrow. Otherwise, converse is not true of this conditional statement. But then the explanation was that, well, since you can come up with this sort of example where 6 is an even integer, is not at all dependent or hinges on 7 is an odd integer. They're two independent truths. independent propositions that have the same truth value. So that's why you would use if then and not if and only if, because they're not related or there's no causation. But then I was like, if and only if doesn't demand causation between the two biconditionals, between the two statements. So, and then I didn't get the answer after that. But anyway, here's the thing, and I showed you the difficulty with this, okay? So I came up with this, and that's the answer. But I'm not completely comfortable with it. All right, next level of difficulty, level slightly harder. Question number 7, determine whether the following is tautology, contradiction, or neither. Remember what tautology is. Tautology is where the entire column is true, 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 true. And contradiction is where the entire column is false, 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 false. Okay? So we're going to do truth tables of this and then see if it's true everywhere or false everywhere, or neither. It's like some true, some false. So it's contingent on the case. So first, we can't think about this without truth tables, so we're going to produce truth tables. So I put these parentheses here because I think it's helpful. First, they're asking you to produce that. That's very simple. That's just normal, very vanilla version of conditional statement. So I'll do that. And the second statement is P and not Q. All right, this is true, false, true, true. Not Q is true. False, true, false, true. P and not Q is true there. Everywhere else, it's false. Now you can start treating this as one logical unit, A, and this as another logical unit, B. The order here doesn't matter. What we need, though, is that both have the same exact truth value, and they don't here. So if they were both false, then the biconditional will be true. Either they need to be simultaneously both true or both false. That's the truth tables of biconditional. And here I noticed that they're never the same thing. So it is false everywhere, therefore it's a contradiction. The whole column is false, so it's a contradiction. So any example, a real example that you come up with, if P then Q, and then you come up with P and not Q, it will be a contradiction. And this is really interesting. Why? Because when the conditional statement is false, it happens only once, right? And it actually happens here, where you have P true and Q not true. So not Q and P. That's where the whole statement is false. So obviously this would be a contradiction. It looks like it would be, but I would still not think about it without the truth tables. First, write down the truth tables. Here you probably realize, wait, this is actually a denial or negation of a conditional statement. This is where the conditional statement is false. So of course this would be a result in a contradiction. All right, now question number 8. Rewrite using logical connectives. So all they have asked you here is to use mathematical symbols to express this sentence, okay, from English to math. First, I see that there's if and only if. So let me highlight that. That's pretty important. So I highlight if and only if. So I split this into 2 parts already, like 2 parts. The first says function has a critical point at x naught. If and only if first derivative at that point is 0 or first derivative at that point does not exist. And then here I have 1, this is 2, and then this is 1. All right, this is biconditional, and the first statement is P, and the second statement is Q or R. So Q is this, and then R is this. So here's how I wrote this. And since I have that problem in level difficulty, then let's go ahead and do truth tables for it too, even though that question didn't ask for it. Q or R. So I'm looking at these 2 columns here, And disjunction is not as demanding as conjunction. Disjunction is true anywhere where either of them is true. Where both of them are true, it's true. It's only false where both are false at the same time. So here and there. So I'm going to say false, and everywhere else it's true. Autopilot mode. All right, so there I have generated one of the proposition's truth values. So this is proposition number 1, this is proposition number 2. So then I can look at it and see if they have the same exact truth values, the biconditional will be true. There, it's false, false, then it is true, false, false, true. So here they have the same truth value. So the whole biconditional is true. Here they don't. Here they don't. Here they do. They don't. And they do. Okay? There you go. That's the truth values for that question, even though they didn't ask it. Now, question number 9. Which is equivalent to the converse of a conditional sentence? Well, actually, the whole question is right here. Which is equivalent to the converse of a conditional sentence. So they're asking you to compare something to the converse of a conditional statement. So remember that this is the conditional statement, if P then Q. Converse of that is switch the spots and don't switch the arrow. So going backward, right? If Q then P. So they're asking you to compare two things to this right here. And what are the two things that you need to compare? Contrapositive of its inverse and inverse of its contrapositive. So you generate these two and then you compare that to converse and see if it's the same. So first you need to generate that. You need to generate contrapositive of its inverse. And it's whose? Converse's inverse. So you start with back here. You start with generating inverse, then contrapositive. Here, you generate contrapositive, then inverse. And how do you generate those things? Well, you just follow the algorithm because, as I said, how do you generate converse? Well, there's an algorithm. You switch the spots, crisscross them, and don't change the arrow. Okay, that's the algorithm or steps or recipe to produce converse. Now, how do you produce inverse? You take whatever you have and you put not or negation in front. You don't change anything else. That's the algorithm to produce inverse. Here I produced inverse of the original statement too, but you just needed this one. So we're working on producing this statement. So I already have inverse. Now I need to get contrapositive of that. And how do I get contrapositive of anything? Again, I get these and I crisscross them and I put negation in front of them. So just close your eyes and think of these as boxes. Just move it and then put negations in front of it. And then whatever you end up with is whatever you end up with. And here it happened that double negation, they cancel, and you ended up with original statement. It gave you back original statement. And how does they ask you to compare this as well as this to the converse of the conditional sentence? So how does this compare to converse? Well, it's not the same. So you just say it's not the same. Now let's generate this one and see how it compares. So I have converse. First, as I said, you need to generate contrapositive. You're starting from right and you go left. So contrapositive first and then inverse. How do you generate contrapositive? You crisscross. So you had Q, then P. So you crisscross and you put negation in front. That's the algorithm or steps to produce contrapositive. Now inverse. How do you generate inverse? Well, you put negations in front and they canceled. So you got the original statement back again. And how does that compare to converse? It's not the same. It's not logically equivalent. So you say final answer, neither of the two options they gave you is the same as converse of a conditional sentence. And that's it. All right, the final question is asking you to determine whether following is tautology, contradiction, or neither. We already solved this sort of a question, but this one is a little bit more involved. So let's start solving it. First, I need to come up with truth values for that, so I can start treating that as one logical unit, and then truth values of this whole thing, and then start treating that as one logical unit, and how I'm gonna go about it. First, and you can start with producing this little bit, then producing this little bit, and then negation of that, and then finally treating these two as logical units and writing down disjunction. This is or connective, right? So now you will treat these as A and B, and then put that together with or. And once you have that, then treat this whole thing as one logical unit, this whole thing as one logical unit, and do biconditional between them. All right, so first I want to work on this right here. So I'm getting not P first. So that's simple enough. It's false, false, true, true. Then not P or Q. So I'm looking at this and this. I just need one of them to be true. And disjunction is satisfied and true. So here, one of them is true. Here, neither are. So this will be false. And everything else will be true. So true, false, true, true. That's disjunction. Then negation of that whole thing. Now start treating this as one logical unit. And negation of that is just reverse it. False, true, false, false. All right, so what have I done? I've done this whole thing right here. So now I need to generate this. And it says not P and conjunction Q. So I'm looking at not P and Q. And for conjunction and connective, I need both of them to be true. And that only happens in the third line. So I'm gonna put true there. Everywhere else, false. All right, now I have gotten this one and this one. So I'm ready to do the final disjunction. Okay, so I'm looking at this and this. And I need both of them to be true at the same time. Oh no, I need disjunction. So I need one of them to be true. So it's true here. Here they're true, and then they're false. And this portion right here is biconditional, very vanilla flavor of it. So I already filled it out because I know you know how to do that by now. So now I'm going to do the final step, which is biconditional between these two blobs. And I'm treating them as two blobs. This is A and this is B. And I'm going to do if and only if between them. And I know that if they have the same truth value, they're true. And if they don't, then it's false. Here, no, mismatched. Here, one is false, one is true. So no. Here, one is false, one is true. No. True, false. No. So it's false everywhere. So we ended up with another contradiction. All right, and that was the 10 problems on conditionals and biconditionals. Hopefully this was helpful. Thank you for watching. Bye.